Membranes.
Membranes.
That's right, membranes. That's what we're going to be talking about today. We're going to be talking about the structures of membranes because we've already talked about fatty acids. We've talked about lipids and all the different derivations of lipids. So today we're going to be talking about membranes. Say membranes.
Membranes.
Membranes. So membranes serve a number of different functions, one of which is that they serve as a barrier. Um, and well, I would guess that's probably the most important. These three structures down here are kind of the way that we talk about and look at membranes from a biochemical standpoint and from a cellular standpoint. Um, they are micelles, bilayers, and liposomes. So a lipid bilayer is probably the most common way that you talk about a membrane, because it serves as your discussion for your plasma membrane as well as membranes in a mitochondria or something like that. And I think a mitochondria is a really great example for how to think about a membrane and how to talk about a membrane, because a mitochondria actually has two membranes, and that's two lipid bilayers. One of them is extremely porous. It's contiguous, so it's like a complete shell around it. But then, so your outer membrane is porous, and I'm talking specifically about a lipid bilayer, a mitochondrial, and I'm going to say LB, lipid bilayer. It's going to be very porous, that outer one is. Then the inner one is extremely selective. It's extremely, not resilient, that's not the word I'm looking for, but it's extremely, selective. So it's going to prevent movement of any number of different molecules. So anyway, point is that lipids or membranes do a lot of different things. They, in addition to serve as a protective barrier, they mediate cell-to-cell interactions and signal transduction. So perceiving an outside message and communicating what that outside message is to inside of the cell is something that the membrane is going to assist with. Now, our three different layers, or our three different kind of levels of discussion, are micelles, bilayers, and liposomes. Our micelles are individual units that have, our individual units in a micelle are generally going to be a head group with a single fatty acid on the end of it. A bilayer, on the other hand, is going to have a cylindrical unit, and it's got a head that equals the size of the side chains. A liposome is kind of a unique structure. It's analogous to a micelle, but it's got an aqueous cavity on the inside. If you think about a micelle, in the interior of it, that's totally hydrophobic, because that's a bunch of hydrophobic tails. Whereas a liposome, on the other hand, you could have a soluble solution, or you could have, you could have a completely soluble protein on the interior of a liposome, compared to a micelle where you're not going to have that. Okay, next up is lipid mobility. So when it comes to a lipid bilayer, you can have a molecule with a head group of, let's just say X out here, and that molecule can flip onto the interior of that cell. So let's say this is outside, inside. This individual molecule can move onto the interior, but it's going to be very, very slow. Movement from one position, A, to another position, B, is going to happen quite rapidly, because we have this constant kind of fluid nature of a membrane. Now, this movement from this transverse diffusion can take place at a faster rate, but it's not going to be something that happens kind of without any sort of outside interference. Temperature dependence of fluidity of a lipid bilayer. So what we have here is, when we are below a transition temperature, a lipid bilayer behaves in a gel-like solid. So at a colder temperature, we're going to have a good bit of space, that all of these individual what are they? Glycerophospholipids, for instance, will occupy. Whereas whenever you go above or to a warmer temperature, all of those lipids are going to mix very well together, and so you don't have this solid gel-like state. Instead, you have this very dynamic fluid state, and that transition temperature is dependent on the chain length and the degree of saturation of its component fatty acid residues. Okay, so whenever you think about this, you think back to what we said about melting points of lipid bilayers. So the longer the chain is, the higher number of carbons in those fatty acid chains is going to have an influence on whether that is a lipid that's in a solid state or a liquid state. Okay, now cholesterol, one of the things that we mentioned about cholesterol is it's going to influence membrane fluidity and it's going to influence membrane rigidity. Cholesterol is going to broaden the temperature range of this phase transition. So it's not, rather than it being, a 5-degree range, it's going to increase it to like a 7 to 10 degree range or something like that.